Good morning. Chapter 19 is called A Model for Light, and it deals with the idea what exactly is light. We know a lot of the behaviors of light because we've made a lot of observations and we've looked at some of those things in chapter 17 and 18, but we really didn't talk about what light is. And that's almost still a bit of a mystery. For up until about Isaac Newton's time, and Isaac Newton believed this, people thought light was made up of a stream of particles. Okay? And that was the predominant theory. But then later, they started noticing that light had lots of wave properties. And so the general consensus was, since it exhibited things like refraction and interference and polarization, that light was obviously a wave. And that worked really well till about 1905. Albert Einstein came along and he explained something called the photoelectric effect. And it was based on the idea that light was made up of little bundles or little particles of energy called photons. So we're back to particles. And then we get the quantum mechanics and the Schrodinger wave equation. And we're back to kind of waves. What we really ended up with, I'm telling you the end of this story first, is something called wave-particle duality. That it's impossible for something to have characteristics of both a wave and a particle. And it turns out that light, which we think of predominantly as a wave, has particle characteristics. It also turns out that little tiny particles like electrons have wave characteristics. That's some pretty high level physics when you start trying to understand wave-particle duality. But in this chapter, we're just going to kind of look at how does light behave like a particle? How does light behave like a wave? One of the first ways we could kind of start to think about it is to look at some of the properties. One of the properties that we know is the property of reflection. However, it doesn't tell us very much about the property. For one reason, we know that if you have a water wave or some type of wave, waves follow the law of reflection. The angle of incidence, this angle here, is equal to the angle of reflection. But so does a ball. If you've ever played pool, if you have a pool ball and it bounces off here, it will go bouncing off at the same angle. So we know that as far as the law of reflection is concerned, it doesn't tell us very much about light because both a particle and a wave will obey the law of reflection. Okay? So let's go on to another characteristic of light. And that's the idea of refraction. If you remember, refraction is the bending of light when it enters a new medium. So maybe if we have something like a light in air, draw it with a different color, it might come in at an angle like this, but then it bends like this when it enters water. So here's our normal. Okay. Well, Newton did think that light was a particle, and he tried to explain the idea of refraction with a particle model, saying that the reason that it bent when it went into the water was because this water exerted forces on it. The problem was, if that was true, then light should have gotten faster when it moved into the water, and in fact, the light traveled slower through water. So the particle model doesn't really hold up when we talk about refraction. but the wave model does. So refraction really is a vote for waves. Okay, this is a wave behavior. And the important part of that we know here is that light slows down when going from air or vacuum into some other medium. Remember, the fastest possible speed of anything is the speed of light, according to our laws of physics. Nothing can travel faster than light, and the light always travels the very fastest in vacuum or in air. In fact, anytime all light travels at the same speed, that 3 times 10 to the 8th, this is in a vacuum, just kind of backing up, all light. And when I say all light, blue light, red light, green light, purple light, ultraviolet light, infrared light, all kinds of electromagnetic radiation. It all travels at the same speed in a vacuum. That 3.00 times 10 to the 8th meters per second. One of the things that we do know from refraction, and I want to erase this, is that different colors of light travel at different speeds. Different colors of light travel at different speeds. If we think about light, I may have enough colors to do this. We start with, generally think of red, that's the longest wavelength, lowest frequency, then orange. I don't have a yellow, so we'll use some other color for yellow. We'll just put yellow, red, orange, yellow, green, blue, green, there's blue, and then violet. Those are the colors in the spectrum. Okay. There's really some important things that you need to understand about how light works. If we're traveling in a vacuum, all of those colors will travel at the exact same speed. But what we find is when we look at their speeds in other substances, they don't travel. This has red light as a lower value for N, which means it travels faster. Let's in some material, doesn't matter which ones, but not air. Then as you cross over to violet light, by the time you get here to violet, for color light, this is going to have the largest value of N, which means it is slowest. In materials. Now, I'm not talking about a huge difference. I'm talking about differences that if red light in a certain glass has an index of refraction of 1.60, by the time you get to violet light, it might be 1.64. Okay. But they do travel, and it's because they travel at different speeds that when we get reflection, if we go, say, into a prism, we shine some white light in here, when it bends and refracts, it gets broken up into that rainbow. I'm going to draw the whole rainbow. But remember, if this is the normal, draw the normal. We're going to get that rainbow as it comes out. And they'll travel it to the inside. Oh well. And then as you keep going, you're going to get all the colors of the rainbow in between. But what I want you to take away from this is red light travels faster, therefore it has a lower index of refraction. Violet light is the slowest, therefore it has the highest index of refraction. You'll remember that when we want to get the index of refraction is the speed in the the speed of light, that's in a vacuum, divided by the speed in the substance or the material. Okay? It's always a number greater than 1. And the slower the light travels, the larger the index of refraction. We talked about the fact in the previous chapter that light travels really slowly through things like a diamond. So a diamond has an index of refraction of like 2.4. Water travels fairly quickly through. It has an index of about 1.33. Okay. All right. All of these refraction characteristics, that's pretty much a wave property, and that really supports the idea that light is, in fact, a wave. Okay? All right. I want you to take away this idea, though. Index of refraction, speed in a vacuum over speed in the substance, and that when we're talking about visible light or light colors, this red light will travel faster and have a lower index. This violet light will travel more slowly and have a larger end. Of course, all the colors in the middle, it just keeps, and it's a little bigger, ends a little bigger, ends a little bigger, ends a little bigger. This is the biggest. Okay, our next property is another one that we think of as being predominantly a wave property that sort of votes in the particle wave. This would kind of vote for a wave also, and that's interference. We know that if I have 2 waves, let's say I take 2 pebbles and I drop them each in a pond. There's 1 pebble. It's going to send a wave out in all directions. Ripples in a pond. But if I do 2, it's going to do the same thing. Same water, so they're going to travel at the same speed. And we're going to get, let's do 1 more for each. These interference patterns. These places where the crests add together are going to look like supercrest. Okay. There'll be other places where it seems as if the wave cancels out, but you've seen patterns like that. Well, it turns out we get really, really similar patterns if we use light. In fact, a scientist named Thomas Young did a very famous experiment. It's called his twin slit interference. And this experiment pretty much convinced the world that light was a wave. He wanted to have two identical light sources that were the same exact color of light, the same frequency. So he decided the best way to do that would be to start with a single source of light. So he has this single source of light. I'm going to let it be a red light source. There it is. We've got this red light source. And he takes it, and in front of it, first he puts just a single slit. So it puts a little grid or something that he's cut this slit in. And he lets that red light, it's going to go through the slit, and it's going to kind of spread out, shine. There's our red light coming through. On another one, and this one, however, he put two slits in. The idea being is he would have two beams of light that were exactly alike. Let me make them a little taller. So now we've got two beams of light. And what you would really expect to see if you have two beams of red light, I'm going to erase this so I have more room. And I put a screen over here, like a movie theater screen or whatever, is that I look over here on this screen. This is what I would expect. I'd expect to see my red light forming two, maybe they're a little bigger, they're a little blurrier, but there's two nice big red things from two beams of red light. That's what you would expect. That's not, in fact, what he saw at all. And now, mind you, I want you to realize these slits are really, really narrow. They are not nearly as wide. This is like hugely magnified. What he saw didn't look like two. It looked like this. I'm going to draw the screen a little bigger because we really need a bigger screen. And let's just look at it head on because it's easier to draw. He found in the middle where these two beams, what you might think of adding together, there was a great big bright red spot, and then a dark spot, and then another one. And then another one on each side, and then another one. Now, the one in the middle, the center one, was by far the very brightest. But it was like red and black, because the places that weren't red would actually be black stripes. Okay. This is a wave interference pattern. This is a place where you have two waves spreading out, and where their crest or their peaks go together, they're adding together. But where the troughs, where you have one upward amplitude and one downward amplitude, this is where they're canceling out. Okay? So Thomas Young realized that a light source, if you had two beams of basically the same light, just like you dropped two pebbles into a pond and you made places where you had kind of super crests where the two wave crests add together, and then kind of super troughs where they canceled out. We have the same thing here. Okay, so he found what we call twin slit interference that light exhibits. Again, if the different colors did make a difference, red light would have sort of the most spread out pattern, whereas violet would have sort of a more tighter, closer together pattern. I'm not real worried that you understand that, but I want you to understand that light beams exhibit interference patterns. You can't see this very well in everyday life, but if I could take you into a lab, it's really easy to demonstrate in the lab. Not one of my options unless I put a simulation. I might put a simulation somewhere where you can see it. Okay. interference patterns, that was supportive of the wave theory. The next one is diffraction. That is also a wave characteristic. Remember, diffraction is when a wave spreads out as it goes around a boundary or through an opening. And we see the same thing. Light, I'm going to put light waves, spreads out as it passes through an aperture. An aperture is like a pinhole or a small opening, or around a barrier. Okay. If we think about that same kind of light source, there's our source of light over here. It's sending out red light in every direction. If I took a sheet of paper and that paper had a tiny little pinhole in it, what I would see is that the light that went through the pinhole also tends to spread out. It doesn't just go out in a straight line. It spreads out. And that spreading out is called diffraction. Now, one thing that you can do at home that we usually do in class, and I'm not sure, if you take your fingers and you hold them, I have a light source over here, really close together, and you hold them kind of low, you can see just the sun, really a window or something works really good. And you look right between your two fingers where they're not touching, you will see little light and dark stripes, like an interference pattern. That's evidence that light is a wave. So hold your two fingers, like your thumb and your forefinger, really close together, and look right between them, and you should see some stripes, like zebra stripes. At least one. Sometimes that's all I can see. But I look through and I can see that stripe in the middle that says, hey, that's a wave interference or a diffraction pattern that I can see. That's called single. What I'm doing here, where you just have one slit, is called single slit diffraction. And what I do, what I see is if this is my finger, and this is my thumb, that in the middle there, when I look right between them, I actually see a little dark stripe. Sometimes I can see like 2 or 3 dark stripes. The light in between my thumb and my finger looks striped, but you gotta hold them really close together, and you gotta look right through the middle of them. So, something fun for you to try at home. Another place that we see interference patterns that's really interesting is with thin films. Thin film interference. You see thin film interference in things like soap bubbles, or if you go outside and you look on a driveway where you might have a little film of oil on water. And the result in both of those is you usually see lots of different colors. You all know that you've been outside and you look and there's a little bit of oil on a puddle in the driveway and you see those kind of rainbow swirly colors. Or anytime you just look at a soap bubble, you'll see those different colors. What's happening is if we have a film where we have maybe some air, and then here we have a little oil, And underneath here we have a little water. Okay. So we have this little thin film coating. When light shines on it, here comes a beam of light. Part of that light gets reflected. Part of it gets refracted and then bounces off and then comes back out. And these two beams of light, or rays of light would be a better word, interfere with each other. Well, we know that different colors of light travel at slightly different speeds, and so when those rays come out, you think of the waves looking like this. Well, different colors are going to look slightly different. And so some of the colors are going to add together, and you may see a lot of blue and a lot of green, and some of the colors may be canceling out and see very little red or yellow. But that's called thin film interference. Thin film interference is used in some different places. We put thin films on sunglasses. We put thin films on my eyeglasses. They put films that are supposed to kind of help cancel out reflections so that so that there's not always a glare when people look at me on my glasses. So that kind of non-glare coating. But all of that thin film interference is indicative that light has this wave characteristic where you have places where the amplitudes add together, and you have places where the amplitudes cancel out. So depending on the thickness of this oil, different colors will have constructive or destructive interference. Okay, there's one more characteristic I think we'll go ahead and look at, and that's called polarization. You've probably all heard of polarized sunglasses. Okay. Light is a transverse electromagnetic wave. Okay, what does that mean? Well, basically, it means that a wave looks something like this. If I use a blue marker to draw the electric field, it oscillates just like a transverse wave. That's the electric field. Okay. Notice it's not just called an electric wave, it's an electromagnetic wave. And we know that the magnetic part also oscillates. So the magnetic part, the symbol for that is a B. It looks something like this. It's oscillating, but it's perpendicular. It's in a different, okay. It's in a different thing. They're perpendicular to each other. We're really interested in the electric field, though, because that's the part that's important in polarization. In polarized light, the electric field should I have said that? Oscillates in one direction. Okay. Most light is not polarized. The sunshine, you turn on your light fixtures, In unpolarized light, the electric field can oscillate in every single direction. So let's think about this. So let's look at an array of light. Normally what would be going on is you'd have this ray of light and the electric field would be oscillating in this direction and in this direction and in this direction and just pretty much any direction you could draw. And so if you had like a beam of light, it would look, here's all this oscillation going on in every direction. Now, if you put it in through what we call a polarizing film, we'll let this one be vertical. This is a vertical polarizing film. If you buy polarized sunglasses, they have what they call a vertical polarization. Polaroid film, and it was made by the people that made Polaroid cameras. They're the ones that first figured out how to do it. What they have is they have these real long molecules, and these real long molecules almost act like slits, and they block everything except for the light. So if you want to picture these kind of long slits, you can't see them. We're talking at a microscopic level. These are long kind of chain molecules. What happens is when light passes through that slit, all of the light coming out is polarized in one direction. So it's oscillating vertically. Okay, so it went through oscillating lots and lots. You cut down the intensity of the light by half. So whatever the intensity of the light was here, when it goes through one film of a single polarizing film, the intensity you get out actually is exactly half the light. So just wearing Polaroid sunglasses blocks half the light. But the real value in having sunglasses that are polarized vertically is when you have reflection off of a lake or off of a ski slope where there's lots of snow, the reflected light is mostly horizontal. That glare is horizontal. So by putting in a vertically polarized light, you block all of this horizontal. There's a whole bunch, usually. You block all that glare. So you get rid of the glare when you wear the polarizing sunglasses. Now, interestingly enough, if I were to take a second polarizing film that was horizontally polarized and put it in, so horizontally polarized, now these molecules are like this direction. And you will get absolutely no light. If you have an old pair of sunglasses, and I've done this before, but I don't have an old pair to show you here. If you put one lens this way and the other one at a 90-degree angle and hold them up, you get zero light through. And if you rotate them till they're in the same direction, you'll see about 50%. So that, same direction, about half the light will go through that. But if you rotate them so that one's vertical and one's horizontal, you won't be able to see any light through those polarizing films. And like I say, the reason we put vertical polarization in sunglasses is because light that's reflected off lakes and hills, snowy hills and those type of things has a lot of horizontal component to it. So it blocks off all of that reflected glare off the lake. Okay, that's all of the notes about this chapter except for the problem solving. I'm going to do a separate video just over problem solving for chapter 19.